Okay, I think we are ready to go now. It's 5 p.m. here in Germany. Welcome again to our today's webinar. My name is Victoria and I am your host today. Before we start, I will give you a few remarks for your information. Please feel free to type in any questions that come up during the webinar in our questions box. You should see it at the top or on the right side of your Microsoft Teams window. The icon should look like a speech bubble with a question mark. We will answer as many questions as possible at the end of the webinar, and if there are too many, don't worry, we will answer each question via email within the next days. Please make sure to let us know your mail address with your questions so we can come back to you afterwards. If there are any technical problems, please don't worry. This webinar is being recorded for you, so you will automatically receive a recording of the webinar within the next 2 days by email. Well, now I would like to introduce you to our today's speaker, Dr. Elena Mukina. Elena studied physics and mathematics at the Yaroslav State University and has a PhD in physics. She has been part of the NETZSCH analyzing and testing family for over 20 years now and has gained lots of experience in our R&D department before taking over the position of the business field manager for the software Kinetics Neo. Elena has been a huge contribution to the development of the Kinetics Neo software, which she will demonstrate today. Welcome, Elena. We are happy to have you here today talking about Kinetics Neo 3.0. Elena will introduce our major release with many innovative new features. I will now hand over to you, Elena, to get started, and my colleague, Dr. Ivan Isayev, will take over our Q&A session afterwards. So make sure to ask your questions afterwards and enjoy our webinar and have fun.
Thank you, Victoria, for the kind introduction. And hello, everybody. Today we have our webinar for Kinetics Neo about the major release version 3.0. It was released last week on 8th of November, and now we have a first week where we use new unique features of our Kinetics Neo software. The main point of our software, or just about new features, are reaction depending on additional parameter. You know that up to now, we make the kinetic analysis based on thermoanalytical measurements, where the main parameter is temperature. However, some reactions depend on another parameters, and we very often have the question from our customers how to analyze the data where another parameter play a role or has an influence on the chemical reaction rate. For example, it could be a pressure. For pressure-dependent reactions, and now we can add a pressure as additional parameter. And here we have 3 examples. The partial pressure of gaseous reactant, for example, hydrogen for metal oxides. And here the main the hydrogen is the reactive gas, and the higher the concentration of hydrogen, the higher reaction rate, and we can create a kinetic model which take into account this concentration. Another one is the reversible reaction, where the gaseous reactant works in the reverse reaction. And next example is the pressure-dependent reaction in inert gas. So sometimes the pressure of inert gas has the influence on the reaction rate. That was a second part. The third part is our thermosets. Here we have a curing kinetic, again with a second parameter. And the second parameter for the curing, for the photopolymers, is the intensity of UV light. We are able to create a common kinetic model where the reaction rate depends not only on temperature, but on intensity of UV light too. Then we have curing reaction with diffusion control. For the data from dielectric analysis and rheology, like, for example, like shear viscosity. We have some flexible data evaluation with arbitrary data, kinetics of incomplete data. We have several new reaction types, and we have some features in user interface. And now about additional parameter. Here in the project, there is a possibility now to use external parameter, and it could be, for example, pressure for different reactions, and with inert gas or with the reactive gas. This external parameter could be intensity of UV light, and of course you can select another parameters as a second parameter where the reaction rate depends not only on temperature but on another parameter. And now about pressure. Let's speak about the second parameter, which is pressure. Here we have three examples. The first one, the pressure of a reactant, which is inside our atmosphere and has some partial pressure. Another one, a reversible reaction, and then inert gas. The first one, if we speak about metal oxide in the hydrogen atmosphere, then it will be reduced to the pure metal. And the higher concentration of hydrogen, the higher reaction rate. Let's make kinetic for the measurements where we have several measurements with a gas mixture. A total pressure is 1 bar, and gas mixture has two components. One of them is inert component, it is nitrogen, and another one is the reactive component, is the hydrogen. Let's see. The data are measured, the measurements are done on our new STA 509 with hydrogen generator. And after the measurement of metal oxide, for example, for tin oxide, we have a pure tin, and it produces very nice melting peak for the second heating. Here for our kinetics, we have the metal oxide with hydrogen, where we have a pure metal and the water. And if the concentration of hydrogen is higher, so if the partial pressure of hydrogen is higher, then the reaction rate will be higher. Here we have kinetic equation where the partial pressure of hydrogen is here before the pre-exponential factor, and here we have activation energy, which depends on the chemical nature of our material and will be not changed because of the partial pressure. We have the reaction rate, we have the pre-exponential factor, which depends on the total pressure. And now here we have a partial pressure of hydrogen and the degree for partial pressure of hydrogen. We will put here the arbitrary value, which will be optimized during our feed. And according to stoichiometric coefficients, it should be 1 here, but according to the reality for the solid reactions, the order of reaction is not equal, is not always equal to the coefficient from our chemical reactions, and therefore we just put here arbitrary value. Let's start. Here we have our measurements. We have two sets of measurements. The first one is measured always at the same heating rate, 20 K per minute, with a different partial concentration, partial pressure of the hydrogen. The lowest one has the slowest one has the lower value of the partial pressure of hydrogen. Here is 33%. The next one is 67%. It is faster, and the next one is the pure hydrogen, is 100%. This screenshot is from our Kinetics Neo software, and the same as all other screenshots on this presentation. The second set is isothermal data for 600 degrees C. And here again, we have three different concentrations or three different partial pressure of hydrogen, 33, 67, and 100%. And of course, for in the pure hydrogen, the reaction is fast, and in the less concentration of hydrogen, the reaction is slow. And now let's go to our software, to Kinetics Neo software. Here we have all this data which are already loaded into the software, isothermal data and dynamic data. Here, this project now has no any dependence on pressure of hydrogen and has no any influence of the pressure in the model. You see here, model based is no any model is present. Now let's go to the project. Then we select external parameter. In this case, it is a pressure. Then we go back, and for each measured curve, we must put a value of the pressure. For example, for 33% of the concentration, we just put 0.33 bar is the partial pressure of hydrogen for this measurement. For the next one, it is 67. For pure hydrogen, it is 1, and the same is done for isothermal data. Now we have this data, and we will create a model. We select the nth order reaction. And for this nth order reaction, we say that the parameters have, that this model must have dependence on the pressure. And after that, we optimize the parameters. Ready. Now we have the model which has a dependence on the kinetic model, which has dependence on two parameters, pressure and temperature. And here are our parameters for this one kinetic model, which can describe all 6 curves. And again, here is our result. And for after optimization of all parameters, we can find that the activation energy here, the pre-exponential factor, the order of reaction is 0.7, and the order of for the pressure, for the partial pressure of hydrogen is 1.2. For verification of this reaction, of this model, we did additional measurements and additional predictions. Predictions were done for the pure hydrogen for the heating rates 5, 10, and 20 K per minute. So these data are simulation, and this data were not present in our data for the analysis. So they will be used only for verification. And now we did a measurement, experimental measurement in pure hydrogen, again for 5, 10, and 20 K per minute. And after that, we compare experimental data and simulated data for pure nitrogen, sorry, for pure hydrogen. And this works well. So it means that we can take our model and make predictions for any temperature program and for any concentration of the hydrogen, partial concentration of the hydrogen. Next example. Here we speak about a reversible reaction and example of decomposition of calcium carbonate under partial pressure of carbon dioxide. The total pressure again is 1 bar, and we use a gas mixture of 2 components. The first is inert component, is the nitrogen, and another one is carbon dioxide. Let's see. Here, for this case, a reaction is reversible. We have a forward reaction and backward reaction. For the forward reaction, we have the kinetic equation with activation energy per exponential factor and reaction type. For a reverse reaction, we have another values here. And after that, the total reaction is the difference between the reaction rate of the forward reaction and reaction rate of reverse reaction. So it means that a reverse reaction will suppress the forward reaction, and therefore the total reaction rate will be lower than it could be for only forward reaction rate. And here is our equation, forward reaction and backward reaction, and we have a total reaction rate. Now with our calcium carbonate, if we have only nitrogen, then there is no backward reaction because we have no any presence of carbon dioxide. We have only forward reaction, and here is our kinetics. We will make a measurement with pure nitrogen with 5, 10, and 20 K per minute. And in Kinetics Neo software, we can create the model which depends on temperature only. And now let's add the dependence on the pressure. Here, that was nitrogen. The second part is the nitrogen with CO2. In this case, if we have a partial pressure of carbon dioxide, then in the presence of carbon dioxide, we have a reverse reaction, and it means that there is the reverse part of reaction and the total reaction will be slow. And if the concentration of carbon dioxide will be higher, or just the partial pressure of carbon dioxide will be higher, then the reaction rate, reaction of a reverse reaction will be higher, and then the total reaction rate will be slow. In order to see how this has influence on the backward reaction, we have here the term is the partial pressure of carbon dioxide power to n, where n is the feed parameter. And now our data, we have firstly pure nitrogen and partial pressure of CO2 is 0. We have 3 curves with 5, 10, 20 K per minute. Then we have partial pressure of CO2 10%. We have again 3 experimental curves, 5, 10, and 20 K per minute, and the third 3 curves are done for 30% of the partial pressure of carbon dioxide. Let's go to our software, open the example with carbon dioxide, this one. Here we have our data, which are independent on pressure and done for pure nitrogen. Here we have the kinetic, which depends on temperature only. And now we will add the kinetic to this model, the dependence on the pressure. Let's go to the project, and for the project we select the external parameter, which is pressure. Then we go back, and for each curve we must set a pressure of the carbon dioxide. Here, for example, for pure nitrogen, for the measurement in pure nitrogen, we have a pressure of carbon dioxide equal to 0. Here, and here it is 0. For the first 3 curves, it is 10% or 0.1 bar. I just switch it on. And for last 3 curves, it is 30%. Here we see 0.3 bar for last 3 curves. I just switch them on, and here we have 3 sets of data for the different heating rates and for the different partial pressure of carbon dioxide. Let's go to the model base. Here is our model, which is independent on the pressure. You see all curves, all simulated curves are placed here where we have pure nitrogen data. Now we will select a new reaction type, which was not present up to now. It is a reversible reaction where forward and reverse reactions both are reactions of nth order. Then we select depending on the pressure, and after that we will make the optimization of this reaction, of this kinetic model, in order to have a best fit for all 9 curves. Now let's see how it works. Yeah. choice. And in this case, we have a model. And here we have a parameter for this model, and this one model with this equation, which is present here, can describe all 9 cores with different heating rates and different partial pressure of carbon dioxide. Again, we are here. Now, a next example, the pressure-dependent reactions in inert gas. Sometimes inert gas has also the influence on the reaction rate. And here is the example. We will make decomposition of calcium oxalate monohydrate under the high pressure of pure nitrogen. Here, the nitrogen is non-reactive gas, and it is not present in the chemical equations if we write them for this decomposition. The measurements will be done in our high pressure STA only in pure nitrogen with the pressure from 1 to 50 bar. Let's go. Here, the first set of data is a normal pressure, 1 bar of our nitrogen, and we make a standard kinetic analysis with different heating rates, 5, 2, 5, 10, and 20 K per minute. Here we have 3 very nice steps. The first step is the release of water from calcium oxalate monohydrate because it's monohydrate. The second is release of carbon monoxide, and the third step is release of carbon dioxide. Here is the classical reaction, is the classical kinetic evaluation for different heating rates where we have only temperature as a parameter. And now let's see what happens with a high pressure of nitrogen, of inert gas. Here we have several measurements where we have always the same heating rate, 20 K per minute. And here we have a different pressure of nitrogen, 5, 10, 20, and 50 bar. We can see that the first step with a release of water is pressure dependent. And here for the higher pressure, we have decomposition at highest temperature. So the higher pressure, then the reaction will be moved to the higher pressure and to the high temperature. And it means that high pressure of nitrogen will suppress decomposition process for the first step here for a release of the water. The second step, a release of CO, a release of carbon monoxide. Here we have no any influence of pressure on the composition step, on the composition kinetics. And the last one is a release of carbon dioxide. Here it is again influence of the pressure of nitrogen. Let's see what happens inside. If we see a little bit more in detail, then we see that the first step and the second step are reversible reactions. And it means that here, during the forward reaction, we have a release of some product. For example, for the first step, it is a release of the water. And then this water react with the calcium oxalate and produce calcium oxalate monohydrate in the backward direction. What happens with a higher pressure? For the higher pressure, we have a lower diffusion coefficient, and the water which is released here during the forward reaction cannot go away from the reaction zone, and the concentration of the water is high in the reaction zone, and therefore the backward reaction will be higher for the higher concentration, or for the higher pressure of the nitrogen. And therefore, for the higher concentration of nitrogen, the backward reaction will suppress the total decomposition step number 1. For the second step, happens nothing. We have here only forward reaction and no backward reaction, and it is not important if we have higher concentration of CO in the reaction zone or not. We have no backward reaction, no reverse reaction, we have only the forward reaction. For the third step, it happens exactly the same like it was for the first step. We have backward reaction, and for the higher concentration of nitrogen, we have higher concentration of carbon dioxide in reaction zone, and then we have the reverse reaction. Now is our chemistry and kinetics. For the first step, we have forward reaction and reverse reaction. For the second step, we have only forward reaction. And for the step number 3, again, we have reversible reaction, and we have forward reaction and reverse reaction. And here, during our simulation or during our kinetic modeling, we can make it a little bit easy just to assume that activation energy for forward and reverse reaction is the same, and a reaction order is the same, and only the influence of the pre-exponential factors, they are proportional to the pressure power to n, where n is our degree of the pressure, and P is the pressure of the pure nitrogen in this case. And the same for the step number 3. Here, P is the pressure of pure nitrogen, and here we have additional part. Let's go to our Kinetics Neo software. Here I will open the calcium oxalate monohydrate. We have here the all data for all pressure. In this case, we have already the project with the external parameter. In the legend, we see not only the heating rate, but we see additional the pressure. For example, for the first line is a pressure equal to 1, and for the last one, pressure equal to the 50 atmosphere. Here, for the last one, it is 50 bar. Here we have 20 bar and all other things. And then we have here the model-based, already created, model-based reaction kinetics, which has 3 steps here. A goes to B, B goes to C, C goes to D. And for each step, we can select if there is dependence on the pressure exist or not. For example, for the first step, A goes to B, the dependence on the pressure is switched on. For the second step, B goes to C. The dependence on the pressure is switched off. It is not present. Here we have only dependence on heating rate, dependence on temperature as usual. And for the last step, C goes to D. Again, we have dependence on the pressure, because here we have reversible reaction and the pressure has the influence on the reversible reaction. And again, here we see that there is a good fit for all data for different heating rates and for the data with, which are measured at different pressures. And it means that here we can take this model and make predictions for other temperature and for other pressure and see what will be the kinetics of our process. That was this example. What is interesting that the parameters of the pressure is 0.7 for the water for the first step and dependent on the pressure 0.7 for the second step, minus 0.7. According to the theory, the diffusion coefficient has dependence on the pressure with the degree -1. But here for the solid reactions, we see that the order of reaction or order of pressure in this case is not equal to 1, which is typical for solid reactions. Next part is the thermosets, composites, photopolymers. Here we have again the example with a second parameter, and a second parameter is UV intensity, where reaction rate, the curing reaction, depends not only on the temperature, but on the intensity of UV light. Here, first set of the data is our temperatures, isothermal data, which are measured on DEA, dielectric analysis. Here, vertically, we have log of ion viscosity. At the beginning, it is low, and then during the curing, the viscosity of material goes up, and ion viscosity of materials increase because the material is not liquid anymore during the curing process. Here, the first data, we did the measurement at the constant value of UV exposure, UV light, UV intensity. And here, the measurements are at 30, 90, and 150 degrees C. And you see definitely for the lower temperature, the reaction rate is the slowest one, and the upper and lower value before and after reaction of ion viscosity is much higher than for other temperature. Why? Because it's a typical temperature dependence of ion viscosity on the temperature. That was a classical kinetic analysis here for the constant value of intensity. And now we can add here the second parameter, dependence on intensity of UV light. Here we have different measurements where the temperature everywhere is the same, but intensity is the different. The slowest one has 36 milliwatt per square centimeter. Here, of course, the reaction is the slowest one. Then it will be higher, 75, then 150, and the fastest reaction has the highest intensity of UV light, and it is 300 milliwatt per square centimeter. You can find the data on they are published, and you can just find it in published paper, the data, but not the analysis. And now it's our data, it's our paper where we are, as NETZSCH, are the co-authors. And now let's go to kinetic analysis. Here we can open the data with dA with intensity. Here is our data, measured data with log of ion viscosity. We have here the first kinetic model, which depends on temperature only and does not depend on other parameter. Here is the first part where we start our analysis. We can see here, for example, the temperature. You can see the temperature 30, 90, and 150 degrees C. And here at the beginning is so-called self-heating, which is also taken into account during our analysis. Okay, here our data. Here is our kinetic model, which is only temperature dependent. Now we will go to project. We select external parameter and select UV light here. And we go to our kinetic model. And for our data, we must put the intensity of UV light. Here is 75 milliwatt per square centimeter for all three data. And now we can switch on dependence on UV light here. The model now is not very nice because the pre-exponential factor is not not use this value 75 milliwatt per square centimeter. We will reduce it maybe by 2, and because it means the log of 2 is about 100. Say recalculate. Now it is very nice. We have our model, original model. Now we will switch on the data which are measured at different temperatures. Let's go here. We have for the first data, see 150 milliwatt per square centimeter, and we put it here for UV light intensity. For 300 milliwatt per centimeter, we put a square centimeter, we put here a value 300. And now let's go to our model and make optimization. Now we are waiting until our total model for the curing of our material will be created. And this model, firstly, this model is autocatalytical model. So if we would like to add additional parameter, then it is not important what kind of reaction type do you have. It could be not only nth order reaction like it was for pressure dependent reactions. It could be, for example, like here, autocatalytical reactions. It could be also the reactions of Avrami with nucleations, diffusions, and so on. You can select any reaction type and make the simulation. And now for a reaction CN, here, autocatalytical reaction CMN, we have a total model which can describe the data at different temperatures and at different intensities as well. For example, here I can show the slowest reaction. Here is UV intensity is 36. Here is the fastest UV intensity is 300 milliwatt per square centimeters. We can just set some in between, and we see that there is very nice description of different intensities. Let's go here to the presentation back. Here are our data. The temperature is 30 to 150 degrees C, and UV intensities from 36 to 300 milliwatt per square centimeter. That was the intensities with different UV light, and it could be done also not only for DA, for DSC as well, and for any different type of measurements which can register your reaction. And now a next example is not about the second parameter, but here we have a diffusion control for DA and Rheology. Up to now, we have the curing. We can make analysis for curing reactions only for DSC. And from the version 3.0, we have a possibility to make analysis of curing reaction with diffusion control, also for DA and for the viscosity. What does it mean, reaction with diffusion control? It takes into account the glass transition inside the polymer. You know that the polymer has a glass transition, and it is a border between two states of materials, glassy state where material is hard and can be broken, and below the glass transition temperature and above glass transition temperature, material is a rubbery or viscous liquid, and it is really elastic. It could not be broken. And if we below the glass transition, then curing can slow, and we must use the slow kinetics for the process, because we are below the glass transition, and above glass transition, the kinetic is different and the curing is fast. The problem is that the glass transition is not always at the same position. For an uncured material, it has the low value, and then during the reaction, it is changed from the low value to the high value. And now for DA and for rheological data, we are able to put the glass transition data here from lower temperature for uncured material to the upper value for the cured material. Here is a temperature as a function of degree of conversion, which is changed from 0 to 100%. And during isothermal curing, we see that at the beginning, our sample temperature is above glass transition temperature, and we have fast curing. And then we have a crossing with the glass transition temperature, we have vitrification, and afterwards we have a sample temperature below the glass transition temperature. We have the curing in vitrified state, and this curing is really very slow. And now we can do this for DAA data and for rheology data. And here we have some very nice example where it works. Now we have a next part is the flexible data evaluation. Firstly, we can make evaluation not only of predefined data type, but on arbitrary data type. Not TGDSC, but also, for example, mass spectrometry, storage modules, concentrations. For this case, we have two new project types for arbitrary differential, arbitrary integral data. Arbitrary differential data will be used for the data where the reaction has a peak like the DSC. It could be, for example, differential thermal analysis, mass spectrometry, or other data. Arbitrary integral data. It could be used for the data where a reaction curve has a step on this curve, like TG. For example, it could be a measured concentrations. You can measure concentration outside of DSC or TG, for example, by optical methods. And after that, you can put these curves into our Kinetics Neo software and then make kinetic analysis. You can measure conversion, degree of conversion. You can measure, for example, storage modules, absorbance during FTIR, and or other integral data. The next point is kinetic for incomplete data. The data are complete if before measurement we have only a reactant and after measurement we have only the product. Then a reaction is complete and completely measured. And then from the last point of the measurement, we can take a value of a total effect of reaction and we can use it for the calculation of degree of conversion. And then the last point of conversion curve is the value which corresponds to the total reaction, to 100% of reaction. We recommend to have always complete data, but sometimes it is impossible. It is really impossible because of different reasons. For example, the instrument cannot go higher than some defined temperature, or you cannot make your material higher above some defined temperature because some other process starts, for example, decomposition of this material, and your main process is not measured. In this case, the final point does not correspond to 100% of conversion, does not correspond to the product of our reaction, but somewhere, sometimes you are able to make a measurement of a total effect of reaction outside of these thermoanalytical measurements by other measurements or other techniques. In this case, you can put this value into our software and then calculate degree of conversion using this data, this value of total effect, and then you will have a conversion curve where final point does not correspond to 100% of conversion. Example here, we have incomplete data Then for each data, we can put, for each curve, we can put the value of the total effect. For example, it could be total mass loss for TG, or total peak area for DSC, total length change for dilatometer, or total signal change for DA or rheometry. And here we have a final curve, and finally we can find the degree of conversion as a function of temperature or time for the curves where reaction is not measured completely. This data, actually, they are nice and they could be analyzed. They could be analyzed by model-based methods. It was up to now and in previous versions of Kinetics Neo software, but now we are able to make a model-free analysis of this data by numerical model-free methods. Here we use 6 curves for activation, for calculation of activation energy, and here we use only 2 curves. For the last part, even here is a very, very nice fit. The activation energy for this last part could be incorrect because the model-free analysis requires more than one curve which is measured at different heating rate or at different conditions. In our new software, we have a new reaction types. One of them is already shown. It is reversible reactions. It was shown for the pressure-dependent decomposition of calcium carbonate. And next one is a reaction of nth order with diffusion. The reversible reactions of nth order, here is a new reaction, this FNR, and it works for reversible reactions where the reaction type of the forward reaction is reaction of the nth order, and reaction type of the reverse reaction is also a reaction of nth order. Then you can use a reaction FNR. Then the next reaction type, new reaction type, is reaction of nth order with diffusion. For 3-dimensional diffusion, up to now it works very well, therefore it is not necessary to change anything. We can just only see on the equations. They are always the same, the only a difference in the part which depends on the which looks like nth order reaction, where we have 1 minus alpha power to n, and n is the order of reaction. So this is very nice. Different models, n is different. We can just select one of them and make a fit very well. But for 1-dimensional diffusion, it is not the case. We have only reaction D1, where we have 0.5 divided by alpha, where alpha is conversion, and it is independent on n. It is independent on the part 1 minus alpha power to n. And now we have created a new reaction type with this additional part. If n equal to 0, then we have a classical reaction of diffusion of 1-dimensional diffusion. If n is not 0, then we have a reaction which is at the beginning has diffusion and at the end has the shape of nth order reaction. Why it is important? Because for many reactions, really for many reactions, we have a shape where at the beginning here, for example, for the main peak, at the beginning, a reaction goes much slower than the nth order reaction. It means that here some diffusion happens. And the final part looks like nth order reaction without any problem. And if we use here our new reaction diffusion with nth order, then we have very nice fit for this type of the curve. It could be used typically for decomposition of polymers. For example, for industrial processes of industrial sintering processes for the production debinding process during production of ceramics or during the metal sintering. It could be also seen for the pyrolysis reaction, where we have some reactions which could not be described by classical reaction of nth order and could not be, of course, described by classical reaction of diffusion. But it could be well described by the new reaction of diffusion with nth order. And now the last item of our new features is a new user interface with a new colorful themes. We have many different themes which you can select any of them. If you would like to work in black theme or in white theme or in gray, you can work in office theme. You can work if you make a nostalgia, for example, with Vista theme. We can just see how it looks like in our software. We can select some black or maybe some Windows 8, or we can select high contrast black, or we can select everything what you want. It could be, for example, Windows 11 or Office, which is the classical Office white, something like this. And you can select everything what you want. The question, next question, which is comes very, very often, how to get this update for the new version. You can just go to the file, to about download, and here you can find a download table. And for some of version, you have here the value download, and for some of them, you have a value request. For if you have download, it means that this version is opened for you. And if it is a request, then it means that this version is not open for you for free. Why it is not open for you for free? Probably your support subscription is expired, and you must ask for support subscription again. If you have here download, then it means that your support subscription is not expired and you can download it right now. So that is everything from our new version of Kinetics Neo software. We have now reactions depending on additional parameters, for example, pressure dependence reactions with a reactive reactant like hydrogen, with a reactive reactant for a reverse reaction in reversible reactions. We have a pressure dependence reactions in inert gas. We can use intensity of UV light as a second parameter for photopolymers. We have curing reactions with diffusion control for DEA and Rheology data, for example, for shear viscosity. We have flexible data evaluation with new arbitrary data types. Incomplete data, we have new reaction types and new user interface. That's all from my side.